Hello students. So after completing few numericals on division by t property, we are gonna take one more numerical on division by t property. Now let me tell you that this numerical is more tougher than the previous one. So here we are gonna see how to apply the division by t property if we get t square in the denominator. So let's see. So guys, here we have to find out Laplace of sine square t upon t square, and as I said that in the denominator we have t square. So how to get the Laplace of this function? So guys, by looking at t square in the denominator, it reminds me about one property, that is division by t property or division by t theorem. So how to get value of this integration by using division by t theorem? So let's revise it. So as per the division by t theorem, here are the two statements. If we have Laplace of f of t upon t square, it means if we have t square in the denominator, then the value of this is given by integration 2 times of phi of s ds and then ds. It means we will integrate this phi of s with respect to s twice, and both times we will be having limits s to infinity. Now guys, how to get this phi of s? So phi of s is nothing but Laplace of f of t, and f of t is the numerator of our function. So my first job is to find out Laplace of that numerator, call it as phi of s, put that phi of s over here and integrate it twice with respect to s, and that will give us the answer. So guys, this property can be extended if you have t cube in the denominator. So that time you have to integrate thrice and so on. So in the syllabus we have 2 integrations, but even if we have third integration, still we can integrate it with respect to s 3 times. Now get back to numerical. So here the numerator, that is sine square t, is my f of t. So I'll call it as f of t. So from f of t we get phi of s by finding Laplace of that f of t. So I'll say finding Laplace on both sides. So on the left hand side we'll get L of f of t, and on the right hand side we'll get Laplace of sine square of t. So now guys, to get the Laplace of sine square of t, there is no standard formula. We have a property to find out Laplace of sine of at, but here we have sine square t. So what we have to do is we have to reduce that power from 2 to 1 so that it will become either sine or cos, and then we can get the Laplace of that. Now for that we have to use the formula of trigonometry. So what is the formula for sine square t, which will convert that trigonometric function from power 2 or degree 2 to the degree 1. So we have a formula, that is Laplace of sine square t is nothing but 1 minus cos of 2t upon 2. Now let's use this formula. So here 2 in the denominator is a constant. I'll take it outside. I'll write it here. So 1 upon 2 outside. In the bracket we will find out Laplace of these two terms separately. So Laplace of 1 is 1 upon s minus Laplace of this cos of 2t is s upon s square plus 4. And guys, I'll call this as phi of s. So here we got the value of phi of s. Now let's use this phi of s in the division by t property to get the answer. So here I'll say using division by t property, here we'll get Laplace of sine square t upon t square as integration from s to infinity, again integration from s to infinity. So I'm integrating twice because I have t square in the denominator, into phi of s, that is 1 upon 2 into 1 by s minus s upon s square plus 4 ds. And now guys, we are going to integrate this function twice with respect to s. So let's start. So first of all, I'll take this 1 upon 2 outside. Integration of 1 upon s, we know it is log s. And for integration of this function, I've explained you in the previous problem that this is a property, that is f dash of x upon f of x, in which I have to multiply and divide by 2, so that here I'll get 2s, and the derivative of s square plus 4 is 2s. So I'll get that derivative in the numerator, and then I can apply the property of integration. So let's start. So here 1 upon 2 outside, integration s to infinity as it is, then integration s to infinity again as it is, first function 1 upon s as it is, minus for the second function I'm multiplying and dividing by 2, so 2s upon s square plus 4, and here I'll multiply by 1 upon 2 into ds. Now let's start with the integration. So 1 by 2 as it is, integration s to infinity as it is. Now integration of 1 upon s is log mod s, minus 1 by 2 as it is. Integration of this is log mod s square plus 4, and this is from s to infinity, and here ds outside. So guys, here I have integrated for the first time, so now this ds will be no more, so I'll be having only one ds, which will be the variable of the second integration. Now let's evaluate this first and then again integrate that function with respect to s. So for that, what I'll do is, here to bring half, here I'll multiply and divide by 2. So it will give me 1 upon 2 integration s to infinity, and this will become 2 into 1 by 2 log mod s minus 1 by 2 log mod s square plus 4, and this is from s to infinity ds. Now guys, what I'm doing here is, I brought half here because in the second function I have half, so I can take that half outside as a common. Then I'll shift this 2 here in the power, because we have a property that is b log a is log a raised to b. Here I'll write down for you. So b into log of a is nothing but log of a to the power b. So as per this property, I can take this 2 here as s square. So this will become 1 by 2 outside, so outside I'll get 1 by 4 integration s to infinity log of s square minus log of s square plus 4, and that is from s to infinity ds. Now this is a property that is log a minus log b, which is log of a upon b, so we will get 1 by 4 integration from s to infinity log of s square upon s square plus 4 from s to infinity ds. Now to evaluate this, if I put infinity directly, then here I'll get infinity by infinity indeterminate form, and since I want the finite answer, what I'll do is I'll adjust this s, and for that reason I'll bring that s in the denominator, so that when I put infinity and when infinity goes in the denominator, we know that any finite number upon infinity is 0, so we can get answer as 0. So for that, let's divide numerator and denominator by s square. So here we will get, it is equal to 1 upon 4 log of, now if I divide numerator with s square, we will get 1, and if I divide denominator with s square, here I'll get 1 plus 4 upon s square. So 1 plus 4 upon s square and guys, limit is from s to infinity. And don't forget that we have one more integration over here, that is s to infinity, and here ds. Now guys, here we will get 1 by 4 integration from s to infinity. Now if I put infinity over here, 4 by infinity is 0. So 1 plus 0, 1. 1 upon 1 is 1. So I'll get first value as log 1 minus, if I put s, then we will get the same function, that is log of 1 upon 1 plus 4 upon s square. And this function we got by making the changes in this function. So I'll straightforward write down this function, which is log of s square upon s square plus 4. And here ds as it is. Now guys, the value of log of 1 is 0. So 0 minus log is negative log. So here we will get 1 by 4 integration from s to infinity negative log of s square upon s square plus 4. And here, if I use the property of logarithm, that is negative log of a by b, it is equal to log of b upon a. So it means that will become positive. So this is nothing but 1 by 4 integration s to infinity log of s square plus 4 upon s square. So I have interchanged numerator and denominator, and I have eliminated the negative sign. Now we have to again integrate this log term with respect to s. And guys, for that we will be using the integration by parts rule. So where we will make the second term as 1. So we have seen this term in the lower standard, that is 11th, 12th, or in the diploma, where if we have one function as log and we want to integrate it, then we don't have any option, because there is no formula or direct property to find out the integration of log. And that is why we bring the second function as 1, and then we apply UV rule, or which is also called as integration by parts rule. So I'll bring second function as 1. So this will become 1 upon 4 integration s to infinity this log of s square plus 4 upon s square into 1 ds. And guys, I'll call this as u and this one as v. Now we all know the formula for integration of u into v. I'll apply that. So this will become 1 by 4 in bracket. Now first term is u, that is log of s square plus 4 upon s square into integration of v. So integration of 1 is s minus integration of, now derivative of u. So the derivative of this log term is 1 upon s square plus 4 upon s square into again derivative of this term. So that will become s raised to 4 in the denominator, numerator s square as it is. Derivative of this is 2s minus s square plus 4, and derivative of s square is 2s into integration of v, which is s ds. And guys, this is from s to infinity. So here I have applied the integration by parts formula. Now let's simplify this. So here we will get 1 by 4. This will become s into log of s square plus 4 upon s square. Here I can cancel this s with s, so here we will get s cube, and then I'll cancel this s square with s cube, so I'll just get s. Now this will become s into s square plus 4. Okay, now let's see the numerator. So here we will get negative inside the integration 2s cube. This is minus of 2s into s square, that is again 2s cube, and minus of 2s into 4, that is minus 8s, upon s into s square plus 4 ds, and this is from s to infinity. Now let's simplify this, guys. So this will become 1 by 4 s log of s square plus 4 upon s square minus, now here we can cancel this 2s cube and negative 2s cube, then we'll get negative 8s, so I can cancel with this s with s. Now negative 8 I can take it outside, that will become positive 8, and in the integration we will get 1 upon s square plus 4, and integration of that is 1 by 2 into tan inverse of s upon 2, and this is from s to infinity. Now guys, here this 8 by 2 is 4 and tan inverse s upon 2. Now we got this function. Now to get the answer, we have to substitute the upper limit and lower limit. So upper limit is infinity. Now if I put s as infinity, I'll get answer as infinity. You can see here that infinity upon infinity is gone. Now give me indeterminate form. And guys, to eliminate that indeterminate form, we have to divide numerator and denominator with s square, so that it will become 4 upon s square, and when I put s as infinity, that infinity will go in the denominator, and we know that any finite number upon infinity is 0, and we will get the finite answer, guys. So that is true for this bracket, but what about the s which is present outside? So if I do this process with the bracket, that's fine, because there I have numerator and denominator, but I cannot do that division process with that s which is outside, and that is why here outside we will get answer as infinity. So guys, the question is how to remove that infinity from here. So to do that, what I'm gonna do is I'm gonna use the indeterminate form properties. So guys, what I'll do is I stop here. I'll call this as equation number 1, and we will move ahead with this first term only, and we will find out its value at s equal to infinity. So let's start. So I'll call this as, let's say, L1. So here I'll say let L1 equal to, now here I have to substitute s as infinity, so I'll apply the limits. So here I'll say let L1 is limit s tends to infinity. This is s into log of, now here s square upon s square is 1 plus 4 upon s square. Now let's apply this infinity. So this will become, first term will be infinity into, here we will get 4 upon infinity, that is 0, plus 1, that is 1. So log of 1 is 0. So guys, it means we are getting a form infinity into 0. And I'm sure that you have revised my videos on indeterminate forms. So there we have covered a numerical like this, where we have infinity into 0 form. So guys, whenever we have infinity into 0 form, what we do is we either convert it into 0 by 0 or infinity upon infinity. Then we apply L'Hopital's rule to get the answer. So to apply the L'Hopital's property or L'Hopital's rule over here, I'll take this s in the denominator. So right now this s is becoming infinity. So if I take that s in the denominator, that will become 0. So I'll get 0 upon 0 form. So I'll show you here. So what we'll do is L1 will be limit s tends to infinity. Numerator is log of 1 plus 4 upon s square, and I'll take this s from here to denominator, so that will become 1 upon s. So see, you have to do adjustment in such a way that if you take this s in the numerator back, you should get the previous step. So if I take s in the numerator, it will go here and I'll get the previous step. Now let's observe here. So if I put s as infinity over here, I'll get 1 upon infinity, that is 0, and here 4 upon infinity 0, 1 plus 0 1, log of 1 is 0, and guys now I got 0 upon 0 form. And now we can apply L'Hopital's rule. So here I'll say by L'Hopital's rule, so by L'Hopital's rule, what we'll do is we will differentiate numerator and denominator separately. So what is derivative of this log term? So here I'll get, so the derivative of this log term is 1 upon 1 plus 4 by s square into the derivative of this. So derivative of 1 is 0 and 4 is constant, and derivative of 1 upon s square, so that is nothing but s raised to minus 2 will be minus 2 upon s cube. So guys, you have to be very well with the derivative. Now let's find out derivative of denominator. So derivative of 1 upon s is minus 1 upon s square. So guys, here I am applying L'Hopital's rule. Now most of you don't know about the L'Hopital's rule, so I'll tell you the L'Hopital's rule quickly over here. So if we have limit, let's say x tends to a for f of x upon g of x, then by L'Hopital's rule what we do is we write this as limit x tends to a f dash of x upon g dash of x, and then finding the derivative, we try to substitute this a and we try to get answer as a finite value, and we try to eliminate the indeterminate form. So here also I'll do the same thing. Now I got the derivative, that is derivative of numerator separately and derivative of denominator separately. Now I'll put that value again and I'll check if I'm getting the finite value or not. So guys, before that let's simplify this itself. So here this will become 4 into minus 2, that is minus 8. This is minus 8 and this is minus 1, so I can say minus 8 and minus 1 constant outside, which will be 8. So L1 is 8 into limit s tends to infinity. Now let's check here. So this will become s square plus 4 and this s square will go in the numerator. So s square upon s square plus 4. Here we have 1 upon s cube upon 1 upon s square. Now guys, here I can cancel this s square with s square, 1s will remain, and I can cancel this 1s with this 1s. Now here I got one more s. So what we can do is we can shift this s in the numerator. So we will get L1 equal to 8 times limit s tends to infinity s upon s square plus 4. Now guys, let's check whether the indeterminate form is eliminated or not. So for that I'll again put s as infinity. So I'll get infinity in the numerator as well as infinity in the denominator. So guys, still we have indeterminate form, that is infinity upon infinity. And if we have indeterminate form, then again I have to apply L'Hopital's rule. And guys, don't worry, this L'Hopital's rule will remain same. I'll be using this property again. That means I'll be differentiating numerator and denominator separately. So let's do that. So here I'll say, therefore by L'Hopital's rule, we will get L1 as 8 limit s tends to infinity. Now the derivative of s is 1 and derivative of s square is 2s, derivative of 4 is 0. So we got value as 1 upon 2s. Now guys, after this again we'll check if we are getting finite value or not. So let's put s as infinity. So if I put infinity over here, I'll get 1 upon infinity, and guys it is 0. So we'll get answer as 0 into 8, that is 0. So we got value of L1 as 0. So guys, you can see here that how I got the value of L1 as 0. So I'll go back to equation number 1. So in equation number 1, we were getting indeterminate form here. So I had considered this as L1, and now I proved that the value of this function is 0 if we put the value, or I'll say the upper limit, as infinity. So from equation number 1, I'll go back to equation 1. Here I'll say from equation 1. Now in the equation number 1, we will put upper and lower limit. So we will get the Laplace of f of t upon t square equal to, so here guys 1 by 4 is constant, I'll take it outside. We will start with the upper limit, so it is infinity. So if we put infinity over here, we have proved here that we are getting 0. So I'll say we will get 0 directly. Next, 8 by 2 is 4. If I put infinity over here, I'll get tan inverse infinity, and which is pi by 2. So we will get plus 4 times pi upon 2. So guys, this is the value we got from upper limit. Minus, let's put the lower limit. So guys, lower limit is s only. So if I put s equal to s, I'll get same function again. So I'll copy down this function. Now after this, I'll take this 1 upon 4 inside, and it will multiply all the 3 terms, and we'll get the final answer. So 1 by 4 into this, so 4 and 4 cancel. So we will get first term as pi upon 2. If I take 1 by 4 here, we will get negative s by 4 log of s square plus 4 upon s square. And if I take 1 by 4 here and multiply this term, then 4 and 4 cancel, we will get plus tan inverse. See here guys, outside this bracket we have negative sign, so negative and positive will become negative. So I'll make it negative over here, the sign will be negative, and we will get tan inverse of s by 2. So you can keep this as final answer, or here you can apply the property again, that is pi by 2 minus tan inverse of s by 2. So guys, we know that tan inverse of x plus cot inverse of x is pi upon 2. So cot inverse of x will be pi by 2 minus tan inverse of x, and here you can observe that term pi by 2 minus tan inverse of s by 2. So s by 2 is like x, so pi by 2 minus tan inverse x is cot inverse x. So here I'll say that it is equal to cot inverse of s by 2, and then minus s upon 4 log of s square plus 4 upon s square. And guys, this is the final answer of the given function. So here we have seen how to apply division by t property twice to a function, and how to integrate 2 times. Also we have learned how to apply L'Hopital's rule if the limit is infinity, or if we are getting indeterminate form. So guys, I'm sure that you like this video, and if you want to learn more videos on engineering mathematics, then do visit to ekeeda.com, and most important is don't forget to share this portal with your friends, because they can also get benefited with such a wonderful explanation. Thank you very much.